Okay, now we have to study the quantum numbers, 4 quantum numbers, and they will be very helpful for the electron configuration. And next slides we will study that. Okay, so let's start here. The electron in an atom is completely described by the 4 quantum numbers, right? This is so N, L, M, and S. We have done that. So to describe the electron in an atom, so we should have 3 or 4 rules we have to study. Okay, guys. So number 1, Pauli exclusion principle. We will need this Pauli exclusion principle. So Pauli, this was a scientist, Wolfgang Pauli, Austrian physicist, and he gave a rule and the Pauli exclusion principle. And we will also study, before Pauli, we will study the Aufbau principle, Pauli exclusion principle, Wundt's rule, and half-filled and partially filled rule. These 4 rules are essential to know the electron configuration. Okay, so what the Pauli explain, first of all, let's say start from Pauli. What the Pauli exclusion principle says: no 2 electrons in the same atom can have exactly the same set of all 4 quantum numbers. So, or one orbital can have maximum 2 electrons. That is the Pauli exclusion principle. So no 2 electron in the same atom can have exactly the same set of 4 quantum numbers. For example, if this is an electron here, this is another electron, this has also 4 quantum numbers same, this has also 4 quantum numbers same, that don't exist. No 2 electrons in the same atom can have exactly the same set of all 4 quantum numbers. L equal to 0, for example, ml is equals to, let's say, -2, right? And ms is equals to -half, let's say. Okay, n is equals to 3 for 1 electron, and the same thing for another electron is not possible. At least any one quantum number is different. Out of 4 quantum numbers, at least 1 quantum number is different. That is the Pauli exclusion principle. Or in the easy way, you should understand that easy way, if you easily describe, one orbital can have maximum 2 electrons, no more than 2. For example, p-1, p0, p1, these orbitals, right? These orbitals, 1, 2, 1, 2, 3. This has maximum 2. One is spin up, one is spin down. This can have maximum 2. One is spin up, one is spin down. This has also maximum 2. One electron is spin up electron, other is spin down electron. So that is, you cannot have 3 electrons in one orbital. You cannot have 3 electrons in one orbital. Okay, that it is saying this. So Pauli exclusion principle. So this is the Pauli exclusion principle. Now after that, so yeah, no more than 2 electrons. So that is the Pauli exclusion principle. So the Pauli exclusion principle also says that the spin quantum number can only have 2 values. No more than 2 electrons can occupy the same orbital. So only 2 electrons can have in one orbital, and 2 electrons should have a different spins. One is spin up and the other is spin down. The spin should be opposite. If one electron is spin up, other electron should be spin down. And maximum it has 2 electrons. That is the Pauli exclusion principle. So see that this is the orbital quantum numbers. Okay, so we have already studied these quantum numbers. So this is just a chart. You can see that this is easy for you. Okay, so to learn the electron configuration, first of all we study the Pauli exclusion principle. Okay, So the electron configuration, okay, now electron configuration means that the arrangement of the electron, distribution of the electron in the orbital. Electron configuration or electron structure, electron configuration, both are same. It means that the distribution of electrons in orbitals. This is the electron configuration. Okay, the energy of the atom orbital increases the principal number, quantum number increases. Okay, so for example, n equals to 1, we already discussed that. Okay, n equals to 2, so n equal to 1 has less energy than the n equals to 2. So if the principal quantum number increases, energy also increases. Okay, and the size of the orbital increases, size become increasing, bigger and bigger. Okay, thus the attraction to the nucleus is weaker and the energy associated with the orbital is higher, less stabilized. Higher means why energy of the higher orbital is more? Because higher orbitals are bigger and they are farther from the nucleus. That's why they have the higher, means the more stable, more unstable. So other is the energy level. If you see the energy distribution, which has more energy, look, so the energy of the orbital increases with the cell. So S is less than P, S energy of S orbital is less than P orbital, is less than D and less than F. Okay, that is another rule. We have to understand that. So then so let's see that. Okay, 1s, then 2s, right, then 2p, and then 3s, 3p, 4s, 4p, 5s, 4p. 3d is less than 4p. Okay, and 5s is more than 4p, and 5p is more than 5s. 4d is more than 4p, right, and like that. Okay, so and the 4s is less than 3d. See that this happens. Okay guys, so this is said to be the this is the Aufbau principle, and the what the Aufbau principle says that. Okay, so the Aufbau principle says that the once while electron is filling, okay, first lower energy level fills first, and left electrons, means that the remaining electrons only fills remaining orbitals. Okay, so if electron is filling, first of all it will fill the lower one and then upper, For example, let's see here, 1s orbital has the less energy than 2s. See that the energy 2s has less than p, 2p, there are 3 2p's, and 3s has more than 2p, 3p has more than 3s. So what is happening? 1s is less than 2s, is less than 2p, is less than, there are 3 2p's. Okay guys, and these 3 2p's has same value. Okay, 2p 0, 2p minus 1, 2p 0, 2p 1, right? There are 3 2p's and they all have same, equals to, sorry, less than, sorry, let me write that again. Okay, so what this is saying, now let's see that here. So this is the Aufbau principle. Aufbau principle says that electron fills in the lower energy level first. Okay, so what is the energy level? So 1s is less than 2s, 2s energy is less than 2p minus 1 is equals to 2p 0 is equals to 2p 1, right? These all are 3 and this is less than 2s is less 2p is less than 3s, 3s is less than 3p minus 1, 3p 0, 3p 1. There are 3p, right? But these are equal, so they are equal in the line, see that. Okay, and that is less than 4s, 4s is less than 4p, 4p is less than 4s 3p, 4s is less than 3d. Look at that, 4s is less than 3d. 3d has higher energy than 4s, interestingly. Okay, 3d and 3d is less than 4p, 4p is less than 5s, like that. So if we have to distribute the electron, first of all we have to fill this guy. If you fill that and the left electrons are left, then we go to the 2s. If 2s is also filled, then 2p. That is the above principle. So the arrangement of the electron is the electron configuration. Okay, so we already discussed that. Okay, so that electron configuration we will write in this form: n s n and x and the number of the electron here. So for example, n s orbital ns, first s, second s, third s, and so here in the power we will write the number of electron. This value can be either 1 or could be 2 maximum, because the one orbital has maximum 2, right? So leave that. Hydrogen has 1 electron, that's why look at that, 1s, 2s, 3s, 2s, 2p, right? 3s, 3p, 4s, 3d, right? Like that. Okay, that's why it has, first of all you have to fill the 1s. 1s has 1s can, every orbital has two electrons, that's why it has 1. That's done. This is the electron configuration of hydrogen. So I already say the off-by principle. So now let's see the off-by principle. Look at that. First of all it will fill the 1s, and then let's say this is the tracking, right? 1s, and after 1s it will fill 2s, and then after it will fill 2s to 2p, 2p to 3s, 3s to then 3p, 3p to 4s, 4s to 3d, and like that. So let's do the electron configuration on this basis of all of these rules. Okay, let's first of all list out the rule. So this is the energy diagram. Okay, so this is the above principle energy diagram. So that is 1. Okay, so this is the above principle energy diagram. It means that first of all 1. Now let me see. Okay, so this is the hydrogen's electron configuration. Okay, so these are others. So we will go to this periodic table also right now, and before that so now let's see, this is okay. We will go to this picture later on after electron configuration and orbital diagram. Okay, so now let's go first to the Hund's rule. Hund's rule. Let's go to the Hund's rule. Hund's rule says that, okay, if electron is filling, then first of all fill electron with parallel spin. So first of all electrons should be filled with the parallel spin and then go. For example, let's say these 3 orbitals. Okay, these are p orbitals. This is p minus 1 orbital, this is p0 and p1, or you can say px, py, pz, whatever, right? So this can have 2 electrons, this can have 2 electrons. We can fill those. These are the rooms, right? Vacant seats 2, 2, 2. So but if you have only 4 electrons, suppose you can get 4 you have 4 electrons, but you have to fill this. How you will fill? Look at that. You have 2 or 3 ways of filling. Okay, one way of filling is this first, and the remaining is this. This is one way. Other way is like that, 2, 2. This is other way. No, this is not correct. First of all, electrons should be filled parallel to all of them, and that if the electron is still you have in the hand, then you go to the anti-parallel also, right? So this is the spin up, and then all should be spin up. Then if you have a more electron, then you can go to the spin down also. For example, if you have a 3 electron and you have to fill those, okay, you have to fill those, for example, and these 3 orbitals, they are empty, for example, and you have to fill these electron here, let's say. So how do you fill that? You have only 3 electrons. You have 3 electrons. How you will fill? You will first of all parallel, 1, 1, 1 to each, done. This is the Holtz rule. Okay, and the other is the half filled rule. Half filled is stable than partially filled. That is another rule. So for example, let's say this is p orbital, 1, 2, 3, and we will take the p orbital in the another scenario. P orbital, this is okay. Now you have, for example, you have the electron like this. Okay, so this, and you have electron like this. So look at that. This is the half filled. This is partially filled, right? So that's why this guy is more stable than this guy. Okay, because p orbital can have how many? 6, right? 2 here, 2 here, 2 here. Total 6. P can have maximum 6 orbital, but you have how many? 1, 2, 3. That's why P6 is most stable. For example, 2p6. This is 2p3. This is 2p2. So this is the partially filled orbital, and this is half filled orbital. That's why this scenario is more stable than 2p2. So that's the half filled and partially filled orbital. So far, so let's list here. We have up to this point we have studied following rules. One is Aufbau principle. This says that smaller, lower energy level fills first, right? According to this guy. First of all 1s, then 2s, then 2p, then 3s, then 3p, then 4s, and then 3d, and then 4p, like that. Second is the Pauli exclusion. It says that no maximum 2 electrons in one orbital, and both should have opposite spin. That means if it is spin up, other is spin down. That is the Pauli. Third is Hund's. Hund's rule says that first of all fill all parallel spin. So if you spin up, other should be spin up, then pairwise them. And fourth is the half filled is more stable than partially filled. This is fourth rule. Okay, so now, so we will go to this picture later on. Okay, I think here we will go. Okay, and now this is, so let's start the electron configuration. How do we do the electron configuration? Okay, so then we will go to the orbital diagram also. after studying the electron configuration. So now electron configuration. Electron configuration. Okay, so how do you do the electron configuration? Now let's take some example. Okay, hydrogen atom. Let's write the hydrogen atom's electron configuration. Hydrogen atom has how many electrons? Just one electron. So electron is equals to number of electron is equals to 1, right? So you go to this picture. First of all, you have to fill 1s, right? Let me write that. So 1s and then 2s, then 2p. 2p are how many? 6. Then 3s, then 3p, then 4s, then 3d, then 4p, like that. Okay, you see, 1s, 2s, 2p, 3s, 3p, 4s, 3d, then 4p, 5s, like that. Okay, so but it has only one electron, that's why 1s1. It has only one electron, that's why that's why 1s1. Okay, now helium, let's say if helium number of electron is equals to 2, that's why again 1s 2, done, maximum 2, right? This is the electron configuration helium. Now let's see the lithium. Lithium is number of electron is equals to 3, that's why it will go to 1s, it will fill 2, and then 2s it has 1, 2 plus 1, 3 electron, done. Now let's say sodium. I will go to directly to the sodium. Let's say sodium number of electron is equals to 11, right? So how it works? So one, look at that, lithium's end at the s, right? Hydrogen end at s, sorry s. Helium also end at s, right? They are ending at s. Now sodium, let's say sodium 11. Okay, 1s 2, only 2 we have consumed 2, then 2s comes, right? 2s2, we have consumed 4 electron, 1s to 2s2. 2p should have, p can have maximum 6, right? px py pg means that 3 times 2 6, that's why 2p 6. Let's say 2 plus 2 4, 4 plus 6 is 10, we have consumed 10 electron, is still 1 left. Then after 2p what comes? 3s, that's why 3s will have 1 electron. 1s orbital has 2 electron, so 2s orbital will have 2 electron, 2p has 6 electron, 3s has 1. Now this is the electron configuration. Okay, so now let's say calcium. Calcium number of electron is equals to 20. Now let's see that. First of all, consume 1s 2, still 18 electron left. 2s 2, 16 electron left. 2p 6, 10 electron left. 3s 2, right? And 8 electron left. 3p 6, 2 electron left, right? And 3p and 3s 3p, then after 3p 4s 2, right? So these all are residing at s. This is also s, this is also s. See that they are s. Now let's say the chlorine. What happens to chlorine? Number of electron is equals to 17, right? Same, 1s2, 2s2, 2p6, 3s2, 3p1, I think, right? 4 plus 6, 10, 12, oh no, 3p5, right? Look at that, chlorine end at the p orbital. Chlorine end at the p orbital. Okay, now let's say, for example, let's say for example the chromium. Okay, chromium number of electron is equals to, I think, 24, right? Chromium is 24. Okay, now let's see that. Okay, Okay, now let's see. So chromium is 24. Yes, I'm right. Okay, yeah, that's good. Chromium 24. Okay, now let's distribute. 1s2 is still 22 left. 2s2, 2p6, 3s2, 3p6, 4s2. This is the calcium, right? 4s2, and after 4s 3d comes, right? 3d4. Look at that. This ended D, right? But look at that here. D can have how many electrons? If you remember that, D can have 10 electrons, right? Means that how many D's? 3, n equals to 3, right? N equals to 3, L equals to 0, 1, 2. If L is equals to 2, then ML is equals to -2, -1, 0, 1, 2. How many? 1, 2, 3, 4, 5. D can have 5, right? This is D. D can have 1, 2, 3, 4, and 5. This can have 2 electrons. 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 This can have 2. So if fulfill, it should have how many electrons? If fully filled, it has 2, 2, 2, 2, 2 means 10 electrons. If it has fully filled, it should have 10 electrons. If it is half filled, it has how many? It should have how many electrons? 1, 2, 3, 4, 5 electrons. If it is half filled, it should have 5 electrons. If it is full filled, it should have 10 electrons. But we have studied one other rule. Partially filled is less stable than half filled, right? So that's why if atom has partially filled, it will try to make half filled. So what we'll do is, nearest closest energy level is 4s1, and what it will happen is one electron go from here to here, and it will become 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, no, 4s1 and 3d5. Both are happy. S orbital can have 2 electrons, that's why half 1 is half of 2. This is fine. And D electron should have 10 electrons, 10's half is 5, that's why it is fine. So instead of this electronic configuration, chromium has this electronic configuration. But look at that here. Chlorine ended P, calcium ended S, sodium ended S, helium ended S, and chromium ended D. Look at that. This is ended S, this is ended P, this is ended D, and some others will indicate F. And now let's see the periodic table, whatever we have. I have last time here. Now let's see here. Look at that. These all are S blocks. So these two are S blocks, first and second. These two are S blocks. Their electronic configuration will end at S. See, these guys are 1s, these guys are 1s, these all are 1s, these guys are 2s. Sorry, these guys are also S. Okay, so now let's see that. Okay, let me see again. Okay, guys, no, that's not correct. Okay, look at that. These guys are S, these guys are S, but this is 1s, this is 1. Okay, this is 1s, okay, and that will be 2s, this will be 3s, these two are 2s, these three are 3s, these will be 4s, this will be 5s, these three will be 6s, these two will be 7s. Means that these guys has 1 electron. So this has 1s1, this has 1s2, this 2s1, this has 3s1, this has 4s1, this has 5s1, this CS has 6s1, francium has 7s1. So beryllium has 2s2, this is 2, right? 2s2, this has 3s2, 4s2, 5s2, 6s2, 7s2. Okay, these guys has s1, 1 electron on the s, but the 1s, 2s, 3s, 4s, 5s, 6s. These guys has 2 electron on the s, but this is 2s, 3s, 4s, 5s, 6s, and 7s. So these guys will indicate D. Okay, guys. These are 3D. These are 4D. these are 5D, these are 6D. Okay, for example, this is 3D3. Okay, chromium, where is the chromium? This is 3D5. Okay, 3D5 because it's a 5. Okay, and similarly like that. Okay, similarly like that. So this is chromium is 3D5 because it was 3D4 actually, but it jumped in 3D. This is 3D4. Okay, 3D3 this is. So this is 3D1, 3D2, 3D3. So just divide if this is third group means -2. 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8, 3D9 and 3D10. Okay, like this. Okay, these are 6. This is 6. 6D1, 6D2, 6D3, 6D4, 6D5, 6D7, 6D8, 6D9, 6D10. So like that. They are the S. And if you think about, they are the P's. These are the P block elements. So their end will P. This will be P1, P2, 2P1, 2P2, 2P3, 2P4, 2P5, 2P6. This is 2P, 3P1, 3P2, 3P3, 3P4, 3P5, 3P6. Like that. Okay. So now, okay. So after that, let's say the orbital diagram also. So let's say orbital diagram. What the orbital diagram? So just the diagrammatical representation of the diagrammatical representation of the electronic configuration. Okay, orbital diagram. Just the pictorial representation. Okay, now how do we pictorially represent? So let's see that. If you take for few example, we will take a box and the spin up electron, we will give the upper half arrow, and spin down we will give upper lower arrow, or we can give just the arrow also fine. Instead of half arrow, full arrow is also fine. So for example, hydrogen has 1s1, right? So just this is, we will write 1s here and we will give 1s up. This is orbital diagram of the hydrogen. So let's say sodium was 1s2, 2s2, 2p6, 3s1, right? This was our sodium. So s orbital is single, it is not further divided. That's why 1s has 2 electrons. One is spin up, other is spin down. And this is the 2s, and 2s has also, s has only 2, right? 2s2, 2 electron. 2p6, but now let's see that the p orbital is, there are 3 p orbitals, right? There are 3 p's, there are 3 p orbitals. Okay, there are 3 p orbitals. That's why for the p we will write this 1. First of all, let me follow the Hund's rule. First of all, parallel, then spin down. 2p6, and you have a 3s1, and for s orbital is just a single box. That's why 3s1. This is the sodium. Okay. Now let's see the chromium as we chlorine. Now let's see the chlorine. Okay. This is the sodium, and now let's take an example of the chlorine. So let's see chlorine, and then we will go with the chromium. Chlorine 17, right? It has a 17 electron. Number of electron is equals to 17. That's why 1s2. This is the electron configuration. This is the orbital diagram. 1s2, then 2s2. Oh, sorry. Oops. 2s2. 2s2, let me write that here. 2s2, 1s2, 2s2. Now 2p6, but the p are further divided into 3. 2p6, 1, 2. Okay, 1, 1, 1, 2, 2, 2. 2p6, 3s2, 3s2 has just 2 electron. Okay, 3p5. 3p, 10, 12, 17, 3p5, right? Now let me fill that 3p5 here. P has 3, right? So 5 electrons are here. That's 1, 2, 3, 4, 5. So 3p5. This is your chlorine. Now let's say chromium. Same as like previous, right? 1s2, 1s2, 2s2, 2s2, 2p6, 1, 2, 3, 4, 5, 6, 1 slow. 2p6, 3s2, 3s2, 3p6, sorry, 3p6, 3p6, 4s2, 4s2, and a 3d5, 3d, 4s1. Okay guys, so okay, chromium, if you remember that chromium, okay, chromium is 4s1 because one electron from s will jump, right? 4s1 and the 3d5, 3d, okay, d orbital has 5 suborbitals, right? 1, 2, 3, 4 and 5. 1, 2, 3, 4, 5 d, right? This is d minus 2, this is d minus 1, this is d0, this is d1, this is d2. That's why 5, right? That is the 3p minus 1, this is 3p0 and 3p1, right? This is 2p minus 1, this is 2p0 and 2p1. So look at that, 3d5, 1, 2, 3, 4, 5, I've filled, done. So this is the orbital diagram. That's the orbital diagram. Okay, this is the orbital diagram. So we have done that. So now this is also orbital diagram. We have done that. This is the boron, carbon. These are examples, and we have already studied the Hund's rule. Okay, this is nitrogen, oxygen, fluorine examples are here. So those are orbital diagrams. Okay, so now let's say study the valence and the core electron. So after that valence and core electron, we will study that in the next chapter. Okay.